Welcome to thermochemistry. Thermochemistry is defined as the study of heat changes that are associated with a physical and or chemical process. To understand this, let's look at the reaction hydrogen and oxygen forming water. What kind of heat change do you think might be associated with this reaction? Well, there are two different processes happening here. In any chemical reaction, bonds are broken and new bonds are formed. That is the definition of a chemical reaction. So this process of breaking bonds actually requires energy. So breaking the hydrogen-hydrogen bond uses up energy, and so does the breaking of the oxygen-oxygen bond also uses up energy. But the bond making process releases energy. So in this case, the bonds that are being made are between the hydrogen and oxygen. So one oxygen binds to two hydrogen atoms, and this usually releases energy. So the heat change that would be associated with this reaction would be this amount of heat that is used up in bond breaking and the amount of energy that is released in the new bond making. If energy released is greater than energy absorbed, you will have a net output of energy, whereas if the energy released is less than energy absorbed, then you will have a net absorption of energy. And it is these kind of energy changes that thermochemistry talks about. What is actually happening has to be experimentally determined, and in this case, we find that the step 2 actually releases more energy than what is required in step 1. Therefore, when water is formed, we can predict that the overall reaction will release energy. Before we go any further, let us make sure that we understand some basic terminology associated with thermochemistry. So the word system is that part of the universe that we are studying. For example, if you were studying a chemical reaction in a beaker, then the mixture, the salt or the ionic, inorganic, organic compound that you're studying is the system. The surroundings are everything else in the universe outside of that system is the surrounding. So the room in which that beaker is placed, the air surrounding the beaker, they are all surroundings. Boundary refers to the membrane that separates the system from the surroundings. For example, in this case, the beaker itself could also be the boundary that separates the reaction from the room around it. Going back to system, we define three kinds of systems: open, closed, isolated. An open system is open to the atmosphere in that both matter and energy can exchange between the system and the surroundings. A closed system is one where matter cannot enter or leave, but energy can, and an isolated system is defined as something that is closed to neither matter nor energy that can interact between the system and its surroundings. An example of an open system could be an open beaker with water. An example of a closed system could be an airtight container, and an isolated system is more of an ideal gas kind of a scenario. So this is a theoretical concept. You would be hard pressed to find a genuinely isolated system. But sometimes during labs, during reactions, we sort of assume that a system is isolated in that matter or energy is not leaving. The closest you can get that in layman terms would be a thermos flask where the water stays warm for a long time because, at least in the beginning, we can assume that no energy is being lost. Again, like I said earlier, it is more of an idealized scenario. There really isn't anything that can genuinely be an isolated system. Okay, there is always eventually some exchange happening. That is why the water in your thermos, even though it is airtight, eventually gets cold. The thermal energy or the heat content is the total amount of energy in a substance, and temperature we define as the average kinetic energy of the particles, not the total thermal energy of that system. Okay, so this is an important point to note. So consider the question, what has higher total thermal energy, a hot cup of coffee or a warm tub of water? Well, the hot cup of coffee has particles that have a higher average kinetic energy compared to the particles in the tub of water. But because the tub of water is so much more massive, as in has a much larger mass, the total thermal energy would be higher in the tub of water and not the hot cup of coffee. One way to think about this is if you mix the two, which one would end up dominating? So if you poured one hot cup of coffee in a tub of warm water, would all the water heat up because of that coffee coming in? Or would the coffee end up losing its heat and coming to the temperature of the bathtub? Hopefully that analogy helps.